Something that's fading from your lives is Morse code. And I don't know if you even know much at all about Morse code. Morse code was a representation of letters using dots and dashes. And with what we're currently doing, all of a sudden you're saying, hey, that's a binary tree. I go left or I go right, left or right. Not necessarily a binary search tree. We're not searching for anything or on and on like that, but it was a way to represent all the letters of the alphabet. Here's E. If you know anything about Morse code, and E is a dot, and I is a dot dot, and A is a dot dash. Hold on for 1 second. Pause record. Hey, so you look over this and you can see by using a binary tree going left or right, I can represent here's X, dash, dot, dot, dash is an X. So if I gave you some code like what you see here, can you decode it? You might have to get your own Morse code somewhere, Google it real quick. Morse code dots and dashes, but can you decode this message? Can you decode it? Yeah. I know what the dash is. The dash is up here. The dash is T. A dot, dash, dash. That bad boy is actually a W. Anybody know the most popular Morse code? Huh? I think the most popular one of all time is S. Oh, yeah, there you go, Emily. Dot, 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 dash, 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 dot, dot, dot. Save our ship. Oh, wait a minute. There's an S. Hee hee. Dash, dash, dash. That's an O. You notice how these letters have different lengths? E is 1 character. W is 3 characters. Well, oh, wait a minute. If that's a W, this is a W. If that's a dot, this is an E. This is an E. This is an E. Dash, dot, dash. That's right there. That's a K. Here's a T. Dot, dash, dash. Right. Dot, dash, dot, dot. That's this bad boy right here. That's an L. And that's got to be an F. 2 weeks left. 2 weeks left in the class. What do you think about that? 2 weeks left. This is really cool now that we know binary trees and how it's represented. And all of a sudden, I start asking questions like, why is E 1 dot and L is a dot, dash, dot, dot? Beep, 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 beep. Why do you think that is? What if I made E a dot, dash, dot, dot, dash? Something crazy. Would that be good? Why would that be bad? Well, I don't know if you remember, but letter frequencies, letter frequencies. I don't know if you remember, but in 161, we did something called Sonnet 18, and we counted the most popular letters. Guess what one of the most popular letters is going to be? E. And why is that? Well, I'd like the more popular letters that are going to be used the most to have less dots and dashes. Because I don't want E to be 5 characters because I'd be typing all the time. Yeah. What do I have between each letter? What's between the T and the W? Say space.
Space.
Space. Yeah, space is a problem. Spaces are a problem. Why are they a problem? Well, these messages are sent in urgency, and we need to get the message across as quick as possible. Now I'm adding not only dots and dashes, but I have spaces in there. Well, do I need the spaces? Yeah, because it breaks it up. Otherwise, it's not decodable. So that gives me a problem. So, what we're going to take a look at today is, well, what if we created one that A, kept down the number of dots and dashes? And of course, we're not going to use dots and dashes. In the computer world, what do we use instead of dots and dashes?
Ones and zeros?
Yeah, we're going to use ones and zeros. And, we're going to, whatever the most popular ones are, we're going to use the shortest amount of, like, what do we want to call it? Sequence of zeros and ones. Well, the first thing we're going to look at is, okay, up here, I have a whole bunch of three things: dashes, spaces, and dots. Okay. So if I counted them all up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18, 21, 22, 25, space 26, 30, 31, 32, 33, 39, 40, 41. So right now, under my characters, I have 41 of them, 41 characters. How many letters do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12. So now if I do 41 divided by 12, I'm going to get an average for the number of characters. I'm going to get the average. 41 divided by 12 is 3. Hey Siri, what's 41 divided by? Hey Google, what's 41 divided by 12? 3.42? Anybody else get that? Hey Siri, what's 41 divided by 12? Siri on my watch says 3.42. So the average character length is going to be 3.42. So if you had a message with 100 characters in, boom, that's going to start to be a lot. So our goal today, the first half of class, is to figure out a way to solve these problems. We want to come up with nice, short representations. We want to get rid of spaces, and we want it to be decodable as quick as possible. Okay? So here's how we go. This is how we want to work on something that is immediately decodable. Immediate decodability, because I don't know if that's spelled decodable. Does that look right? All right. So the first thing is we've come up with a new language. Okay. A new language. And this new language only has a couple of letters in it. A, B, C, D, and E. All right. So the first thing we're going to do with these characters is come up with a weight. You'll see how this comes into play. So we're going to calculate the character weight. So if I took a look at this language, and some of the words are bead, cab, on and on and on. And I did that same thing I did before when I did my letter frequencies in Sonnet 18. And I said, okay, out of all these characters, A actually comes up a nice even number. It comes up 20% of the time. B is not so popular. It's about 10% of the time. C is about 10% of the time. D is a little more common in this language. It comes up 15. Oh, and E is the ever popular E. It is everywhere. Now, we would want to do this with A through Z. These numbers wouldn't be as nice. These numbers are nice, right? They come out even. So for this first example, so we got that. Okay. And we also know that 20% is 0.20, 0.10, 0.10, 0.15, and 0.45. Now we are going to create code. We're going to create our own dots and dashes for the letters A through E. We're going to do zeros and ones, but we're going to come up with our own system. So, how do we do this? Well, we start with the smallest two, and we're going to build a binary tree, a goofy looking binary tree. The smallest two percentages we want to have near the bottom, right? E is a good percentage. It's near the top, so it's less. Some of these others that are bad, we want near the bottom. So we're going to put B and C down here on the bottom. And B is 0.10, C is 0.10, and we are going to join them. When these two are together, they become a 0.2. Okay, so these two became a 0.2. Now, I need to keep doing this same process. And B is done and C is done, but it made a 0.2. My next smallest is 0.15. So I combine that with either the 0.20 for A or the 0.20 for these two. I think I'm going to combine it with A. So I'm going to take D, it's a 0.15. I'm going to take A, it's a 0.20, and that's going to make up a 0.35. Okay, so this guy and this guy are now off the board. On my board is the BC, which is a 0.2, or the DA, which is a 0.35, or the E, which is a 0.45. My next two smallest are here and here. They go together and give me a 0.55. And finally, I'm going to add the E on because that's my last smallest one. And I'm going to get a 1, 100%. Sort of looks like that Morse code I was showing you a little while ago. All right. What am I going to do now? Zeros to the left, ones to the right. Zeros to the left, ones to the right. Ooh. Letter A is represented by 011. Letter B is represented by 0, 0, 0. Letter C, 0, 0, 1. Letter D, 0, 1, 0. Letter E is just a 1. Now, this thing is called a Huffman code. Its advantages are it's going to be short in length. For example, I'm going to look at something called the expected length. The expected length is going to be, well, let's see. A is 0.2, but A is also 3 characters. It's 0.1, and it's also 3 characters. C is a 0.1. It is 3 characters. B is a 0.15, 3 characters. And E is a 0.45, and it's 1 character. 0.6 plus 0.3 plus 0.3 plus 0.45 plus 0.45. That's 1.2 if I add the first 3, and that's a 5, excuse me. 0.9, 2.1 is my expected length. I have an expected length, assuming that E is coming up 45% of the time, C is coming up 10% of the time. So when I do a message, the expected length, boom, one of the things I wanted to do was to get this down from, what did we have on the last page? Oh my, 3.42. So that was the first thing. The second thing, the spaces are going to be gone. And the third thing is I want to make it decodable. So if I gave you a message and I did something like 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, could you decode that and notice that I didn't put any spaces in there? Oh, which one of them is just 0? None of them. Is there one that's 0, 0? Nope. Is there one that's 0, 0? Yep. B. Nothing is just 0. Nothing is 0, 1. Up A. 3 zeros again. B. And finally an E. How about that? To me, that's kind of cool. If I sent you this string of digits that, by way of our secret numbering system, you know this is the word babe. You wouldn't even have to tell anybody else. It's your secret word. You want to do another one? Yeah, let's do it. Got it. All right. Give me another one. Example number 2. Keep it alphabetical. We'll go from A to B. We have C's and D's. We have E's and F's. We even have G's and H's. Crazy. One thing I do need to do is make sure my percentages add up to 100. Need to make sure my percentages add up to 100. Give me a percentage for A. There's 8 of them. So let's keep them between 10 and 20%. Give me an A.
10%.
10%. B, 12%. C, 12%. D, oh, 8%. We better keep track. 22 after that, and 12 is 34, and 8 is 42, which is about 58 to work with. E, 20%. That gets me up to 62. Still have 38 to work with. F, 12%. Another 12. That gets me to 74. D, 3%. It gets me H, 18%. Okay. Build the binary tree. Build the binary tree. Take the two smallest. Here's 8, and here's 8. D is 0.8. G is 0.8. They come together to give me a 0.16. So this is off the table and that is off the table, but 0.16 is on the table. What would you like to combine next?
I mean, we have to combine A with one of the 12s.
Yeah, exactly. Which one do you want to combine it with?
Let's go with B because that's probably used left off, and then C or
Sure.
F.
B. So this guy and this guy give me a 0.22. That's now on the table, but A is off and B is off. What's my next two smallest?
C and F.
C and F? Yeah. C is 0.12. F is 0.12. That's going to give me a 0.24. Hmm. So what did I just do? C is off the table. Okay, so I have a 0.16, 0.22, a 0.24, a 0.20, and a 0.18. What would have to be next?
Combining H with 0.16.
Yeah, I'm gonna have to do H, which is 0.18, and combine it up and get a 0.34. So H is off the table. Uh-oh, I got a little tightness coming on here because I'm gonna have to do E with what?
0.22.
Yeah. So boy, let's put E in here and we're gonna go up. E in 0.22 gives me a 0.42. Oh crap. I need to move this guy over beside him, don't I? So now I have H, D, G. I need to move C and F over, and then I have the A, B, E. And this goes up to 0.34, 0.16. We got that one. Got this one. This and this come together to be 0.24. ABE, this and this become 0.22. That's an ugly E. When I add the E, I got a 0.42. I'm running out of room again. These two combine, 0.58. And finally, these two combine to give me my 1. Sorry, a little sloppy, but we got her done. Add in zeros and ones. 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1. Oh, hey, Pauloy. All right. A, B, C, D, E, F, G, and H. And then we're looking for the expected length. May not be the actual one, depending on the message that's being sent. Here's 100. B is 101. C 010. E 0010. 0010. E. E is nice. 11. F 011. V 0011. And H 000. Okay. Working on my expected length. A 3 times 0.1. That was 10%. Plus B, which is 3 times 0.12. Plus C is 3 times 0.12. D is 4 times 0.08. E is 2 times 0.2. F, 3 times 0.12. G is 4 times 0.08. Woo! H, 3 times 0.18. What is the expected length for each character? I don't know. 0 0.3 plus 0.36 plus 0.36 plus 0.32, 0.4, 0.36, 0.32, and 0.54. Oh boy. 0.66 added the first two, 0.68 added the second two, 0.76, 0.86. I don't know the calculators, so 14 carrying to 1.32 and to 1.62, 2.94. Oh, unless I messed it up. The more characters, the longer this is going to be because the more options. And of course, now could I give you a message 0110110101001101010, and you could immediately decode it? The answer would be yes. The answer would be yes. Should I do one? Should I make something up? Or are you good? Okay. I will take silence as you did a great job teaching this. We can move on. Again, this is the expected length. If I gave you a message, we would take the number of digits divided by the letters to get the actual length. You good? All right. I must be tearing it up today. Okay. Second thing I'm going to do, I can use more plain paper. This is something called tree balancing today. Tree balancing. what do I mean by tree balancing? Well, if I asked you to build a tree and I said, here's how I want you to build a tree, A, B, C, D, E, F, G. Well, you would say A, B, C, D, A goes here, B goes here, C go, oh, this is not a good tree, is it? It just keeps going to the right. We don't like it. Well, these two guys, hey, you guys, Adelson, Velsky, and Landis came up with this AVL, of course, that's their initials, AVL, to help us do tree balancing. All right, we're going to give this a whirl. I should probably do it with some numbers first before the really hard one. So I'm going to do it with some numbers first and how Adelson-Velsky rebalancing is a question on the final exam. Match the name with what they did. What did Huffman do? We just talked about Huffman codes. Okay. What did Adelson-Velsky do? Adelison. Tree balancing. All right. So I'm going to give you some numbers. 14, 16, 4, 6, 8, 10, 9, 5, and 1. And what we're going to do is build a tree, but not one that could possibly end up like this. Not possibly end up like that. And what can, well, we're going to see in a second how we do this. First number I put on my tree is 14. Now, each one of these is going to have something called a balance factor. All right. Note to self, a balance factor. As we're doing this, think about how you would code it. Balance factor, we want to have a 1, a 0, or a -1. And this is laid out in the NIOF book. How do I get a balance factor? I take the left subtree height and subtract the right subtree height. All right. So for this first guy, I say 14, and I'm going, yep, the left subtree minus the right, that's a 0. That means we're happy. If I wanted to search this binary tree, it would be great. Next number I'm going to add is 16. 4 now has a balance factor of 0 minus 1. So that's -1. 16 has 0 minus. We're okay with that. We like those numbers. Next number I'm going to add is a 4. 4 is less than 14. It goes to the left. 16 was greater. It went to the right. Looking at balance factors, I have 0, 0, 0. Everybody's happy. The next number I add is 6. 14, 4, 16, 6. All right. Subtree height is 2 minus 1. That's a 1. 0 minus 1, -1. 0 minus 0 and 0. Still happy. I have my balance factors check out. Again, I'd have to have a bunch of code written to figure out how big is the subtree so I could get everybody's balance factor. I'd have to traverse down and something that I think was a challenge earlier that we didn't really do much with. So 14, 16, 4, and 6 are off the list. Next thing on the list is an 8. All right, so now I have 14. I have 4 to the left, 16 to the right, 6 to the right, and now 8 is going to the right. I look at balance factors right now, I have a 2. Ooh, I have a -2, -1, 0, and 0. Is everybody okay with what I just did? So Adelson-Velsky must have done hundreds of these to pick up patterns before you could actually code it. And more, this class is like, oh my goodness, it's pick up a pattern, pick up a pattern, pick up a pattern. Now I can write the code. Well, when I added the 8, things became unstable. And what they now say is we're going to go to the node before. And since this is a right child, we're going to do a rotation. We're going to do a left rotation. Okay. The left rotation is I'm going to rotate this way. So now what I have is 14. I have 6 because it rotates up. 4 goes to the left. 8 goes to the right. 16 goes to the right. And when I check my balance factors, I have 1, 0, 0, and 0. Everything is happy. So by making one quick adjustment, this is a left rotation. Everything's good. Now, we're going to look, oh, left. Is that like Def Leopard? No, we have left rotation. Well, I'm assuming if there's a left rotation, there's a right rotation. There's going to be 2 more. The next one is called a left, then a right rotation. And finally, a right left rotation. Edelson-Velsky came up with these are the 4 you need. Right here, we just did a left rotation. Things were not good with my balance, so I had to do a rotation. Oh boy. What was my next number that we wanted to add on to here? We just added 8. We want to add 10. We just added. So now we're going to add 10. 14, 6, 4, 8, 10, 16. Start looking at balance factors. Oh no. There's a 2. That one's easy. That's a 0. That's a 0. 1 minus 2, that's a -1. A 0 and I'm -1. Something's going wrong. And this time and I haven't picked up the patterns yet, but I know I need to do a left rotation and then a right rotation. I need to do a left rotation. So that's 1. This is 2. The left rotation is going to be here with the 8. It's going to rotate up. So I should have something that looks like 14, 8, 6, 4, and the 10 sitting, oh, there's not much room. The 10 sitting here and the 16's here. So step one was a left rotation. Still unbalanced. It's still unbalanced. This guy up here is still a 2. So even though I just did the left rotation, I now need to do a right rotation, which is going to put, I'm running out of room, which is now going to put 8 at the top. Here's 14. Here's 16. If 8 went to the top, what happens? Well, now the 6 stays attached here. Here's the 6. Here's the 4. But the 10 has to go over to that guy. The 10 is going to go and attach to become his right child. So now this is the right rotation. It did a left rotation, moved the 8 up. We weren't done. It does a right rotation, moves the 8 up. But this 10 has to come down and be the rightmost child of 6. That was, my friends, a left-right rotation. I can build a tree, not bad. I have to figure out how to count the balance factors. I have to keep track of where I left off. I added the 10 and then stuff went crazy, and how I would move and reconnect those. Is this tree now searchable as efficient as possible? And the answer is yes. All right. For those of you, Adelson Velsky, tree balancing. For those of you that have the NIOF book, you'll know there's a big example in there, and it's going to use states. It's going to use Rhode Island, PA, Delaware, Georgia, Ohio, Massachusetts, Illinois, Michigan, Indiana, New York, Vermont. I think there's some more going on there. But let's, again, our balance factors are -1, 0, and 1. Final exam test question. Whoop, there it is. I'm going to give you about 2 minutes, let you get a head start on building this tree so that it is a balanced tree. We want it to be a balanced tree. All right, all right, so hopefully after the first 3, you have something that we added Rhode Island. PA went to the left. Yeah, my balance factor became a 2, a 1, and a 0. And I had to do that right rotation this time. So after the first 3, do you have something that looks like that? I'm going to add Georgia. Georgia. In my head, I'm doing 2 minus 1 is 1, -1, 0. I never have to really count the leaves because they're always going to be 0. If I was writing the code for this, note to self, don't count the leaves. Ohio. O is less than P, greater than D, greater than uh-oh. I got to Ohio, and this became a 2. This became a -2, -1, 0, 0. So I need to do a rotation. I need to do a left rotation. PA, Georgia, Delaware, Ohio, Rhode Island. I did a left rotation on Georgia. And I'm looking at my balance factors and I get 1, 0, and all the nodes. I only had to check 2. This one is a 1, and this one becomes a 0. So all I needed to do was that left rotation. I didn't have to do another right rotation. Ohio is off the board. It's like driving down the road looking for license plates. You did that evaluation at the beginning of class. You can also do the rate my professors. I get a kick out of them sometime. Gives you a chance to be honest. Then I find out if you like me or not at all. Meanwhile, back at the ranch, Massachusetts, left, right, left. New balance factors. This guy is now a 1. This guy is now -1. This guy is a 2. So I'm going to have to do, and it looks to me when I do the left, this is going to go down and be long, and I'm still going. So the first thing I'm going to do is the left. Okay. The left gives me PA. Ohio is here now. Okay. Then we go Georgia, which stays there. Delaware, which stays there. And this Massachusetts is still over here after I did the left. I do the left. Ohio goes up. And these two go down, and Massachusetts hanging here. We still have PA and Rhode Island. But I have still an unbalanced tree. There's that 2. So if I just did a left, I now need to stay with that node right there and do a right. When I do this right, this guy, whatever's over here in this subtree, is going to attach to here. The one right below the one rotating up. Ooh. So Ohio goes up, working with the left side. Ohio goes up. This is still Georgia. This subtree attaches to the right. So there goes Massachusetts. Here comes Delaware. Over here is PA and Rhode Island. No, I had to do a left, right. Unbalanced tree that's not balanced, I do it again. I attach this right subtree to this guy right here. Ohio goes up. I need to attach it to, so he may have a something here. So Massachusetts is going to go all the way to the right. Oh my. Baby steps. We got up through Massachusetts. Now it's going to be less rotatings because I'm going to start to have more locations and so forth. Put a couple more in here. Illinois. I is to the left, to the right, to the left. A, B, C, D, E, F, G, H, I. So Illinois would go here. 3 minus 2 balance factor is okay. Michigan is actually going to go here. So I'm now going to start to be able to add more and more. Fortunately, I have lots of room to add. I don't have to do so many rotations. Indiana, Hijklmn. Oh boy. Indiana would go there. 1, 2, 3, 4 minus 2. I now have a problem. I have a -2 up here. What do you think I would have to do at this point with Indiana here? What are your thoughts?
Maybe we have to put 2 on the right somehow.
Yeah. Yeah, I mean this is a good question. It's not an easy question. The last one I added was Indiana. And I'm somehow probably going to have to get up here and say, do a left rotation, which moves Indiana here, then do a right, one, yeah, lots of playing going on right now. There's room over here, so it's not like I have to go all the way up, but I need you to get the basics of what's going on. More of this is in the book. Keep going on and on and on. Yes, somehow Massachusetts is going to have to go to here. So we have Georgia and Delaware, and then oh yeah, oh boy, we have a couple things going on there. Do we have any questions? That was a lot of good stuff today. Huffman trees, Adolfsonvelsky balanced tree. Trees, trees everywhere. Can't see the forest.